Alright, so let's complete this section by having a very brief discussion on the origin and application of differential equations. This is fortunate because today I am not really feeling that well, so that I can solve some problems. And the fortunate thing is that in today's discussion, truly speaking, there is no mathematics, it's simply a discussion. So the discussion is about the origin and application of these differential equations. We have already classified them. We have gone through a very rudimentary classification scheme, linear, non-linear, these things. But where do these equations originate? Are they simply mathematical curiosities, or do they have some kind of physical origin, chemical origin, biological origin? Yes. So the author has given a brief list of places, or actually some problems taken from other subjects, other areas where this type of equations arise. So let's see the brief list as given by the author. These equations arise in the problem of determining the motion of a projectile or rocket or satellite or a planet. We already know about these things, okay. For example, at some stage you already have encountered classical mechanics, Newtonian mechanics. There you have studied a little about these things. Say the motion of a projectile, when you throw a rock, say, not exactly straight up, not vertically upwards, but say at an angle. You know that after reaching some height the rock comes down, but in doing so it moves along an arc, and you may already know that that arc is a parabola. How do we know this? From where do we get the knowledge that the arc is a parabola? From experience we know that the rock would go like this and eventually it comes down like this. But how do we know that it's really a parabola? I mean, there are other arcs also, other curves also, which are like this but which are not parabola. So we know that from a differential equation, by solving a differential equation. The solution tells us that the arc has to be a parabola, provided of course we neglect air resistance, those things are there. Similarly, one has the motion of a rocket. When a rocket starts its ascent, it goes straight up, of course. It does not immediately start tilting. If it does, then it will explode for some reason. I am not exactly clear, but I have seen this on videos. It will go straight up, and then after some time, after reaching some height, it slowly starts tilting. And then, so it also describes some kind of curve. It doesn't just go straight up throughout its journey. That's not what it does. So how can we study that motion? There are equations. Those equations come from those equations or those functions which tell us how the path of the rocket should be. That thing itself comes from some differential equation. We can also similarly study motions of satellites or planets. You probably already know I'm almost sure you know that the planets, our planets which move around the sun, uh, do so in an elliptical orbit. It's not exactly circular, with the sun situated at one of the two foci of these elliptical orbits. Where do we know that from? Again, from some differential equation. Let's see the second one. The problem of determining the charge or current in an electric circuit. Electric circuit, electrical circuit. Well, charge and current are two different things. So, if you have an electrical circuit, say you know its elements, say you know how much resistance is there and those things, voltage, all these things from electricity. How do you determine that this much current is passing through that circuit or this much charge is involved in that system? That also is determined by some kind of differential equation. Number 3, the problem of conduction of heat in a rod or slab of metal or a rod made of some kind of metal, some material. You have already seen that on the streets there are people who make street food, right? And they use some kind of flat surface, metal surface, which they are heating from below, and on that they cook whatever they want to cook. So the thing is that when you are heating something, okay, when you are applying heat to some kind of material which conducts heat, then slowly it becomes hotter and hotter. How does heat flow through that material? And the problem is that, say, a source of heat is there. At a given point of your slab or rod, at a given instant of time, what is the temperature? Is there any way of saying what the temperature should be at this instant of time and say at this distance, at this point from the heat source? Yes. And that knowledge also comes from solving a differential equation known as the heat equation. Again, a differential equation. Number 4. The problem of determining the vibrations of a wire or membrane. If you take a wire and hold it taut, and then you pinch one part of it, you lift it to some height and then release, and there is vibration. Okay. The same thing you can do in a membrane also. How to determine what type of vibrations will that material suffer, what will happen? We know from experience that these vibrations eventually die down. But where is the energy going? what is happening. So all these things can be determined from some kind of differential equation. Again, differential equation. Number 5, the study of decomposition of radioactive materials or the study of the rate of growth or study of growth itself of a population, human population, rat population, mice population, any kind of population. You know that there are radioactive materials like uranium, for example. What happens is that you can imagine that because in the nuclei of these materials there are so many protons, right? There are protons, there are neutrons. The neutrons are electrically neutral, the protons are all positive. These are some simple things from physics that we all know. So you can imagine that if there are protons in so close proximity inside the nucleus, they are repelling each other. So why do they not just simply fly apart and the nucleus just simply disintegrates? Why does this not happen? Because that should happen, right? They are not attracting each other, as opposed to that they are actually repelling each other. So the answer is your strong nuclear force. That overcomes that electrostatic repulsion. But what happens in these radioactive materials is that the number of these repelling particles, protons, it becomes so large that some things leak in the form of radiation. So that is your decomposition of radioactive materials. So if you just simply leave a piece of radioactive material, slowly over time, it will release things in the form of radiation, and in doing so, its radioactivity will come down. Essentially, it is losing things. How does that happen? And we are not talking about the physics or anything. In a given amount of time, how much material is lost in the form of radiation? Can this be said? Can anything be said about that? Yes, we can say so. And that itself also comes from a differential equation. Similarly, we can say something about the growth of a population. Say you know that the population of a country was this in this year, and then it grew to some larger number in this year. From these studies, you can formulate some kind of differential equation that will predict most likely what will happen in future. But simply by looking at the differential equation, you perhaps won't be able to say anything about the population straight away. You will have to solve the differential equation. We are coming to that. Okay. So again, a differential equation is involved. Then of course, the study of reactions of chemicals. And here also we are not talking about why these reactions happen or the chemistry of these processes, but rather at what rate a reaction happens, this kind of things, chemical kinetics. There also we encounter differential equations. And one more, the study of curves with certain geometric properties. That's essentially just geometry, study of curves with some given geometric properties. But here also differential equations help us. And a differential equation can capture a property that is satisfied by many curves, in fact probably infinitely many curves. So the differential equation alone tells us that here you have a family of curves where there are infinitely many members, all of them have that property. Okay, so these are some places where differential equations arise. So far we have simply just said that they arise, but why do they arise? Exactly why do differential equations arise and not ordinary equations? See, in many of these examples, and of course there are innumerable others which the author has not mentioned, there are quantities which are varying, and they are varying with respect to some other quantities. Say you change one quantity, something related to this quantity changes, and these processes or these things happen obeying some kind of physical laws, chemical laws, and in these laws rates of change of these quantities are involved with respect to some other quantities, and these rates you already know are derivatives. So the laws themselves give us, or in fact become, when expressed mathematically, equations involving these derivatives, but that just by definition are differential equations. So that is why differential equations arise in this type of thing. Wherever there is any kind of change, most likely there will be a differential equation in the background which governs that change. Now, when you see, how does it start? Say someone wants to study how heat is conducted in a conducting material. That rod, say you have a rod or you have a cooking slab which you are heating up from below, and you want to study how heat propagates through that material. What will you do? You will of course have some kind of physics behind it. Studying that physics, you will figure out that you have to do this. You have to consider this rate of change, and this rate of change is related to something else, that rate of change, by some kind of equation. Now what usually happens is this: see, nature is very complex, extraordinarily complex, so complex that if we really have to take into account every small detail, first of all we cannot do that actually. Truly speaking, we cannot take into account every small detail. Even if you are able to take into account small details and you formulate a kind of equation which is a differential equation, it may be so complicated that it will simply be useless. You won't be able to use it to conclude anything. Probably it's really capturing the reality of that thing very accurately, but it becomes useless. So what we do instead is that in the beginning itself, while formulating the problem mathematically, we make some assumptions, some simplifying assumptions. For example, when I said that we throw a rock, okay, so the rock follows a parabolic path and then it comes down. So here itself there is a simplifying assumption. Namely, we assume that there is no air, that the rock is being thrown in vacuum, which is not true actually. There is air. So whenever there is air resistance. If you take that into account, then the equation becomes very complicated and its solution becomes very complicated, and the path is actually not parabola, slightly something else. However, in most of the cases what happens is that the accuracy that we need is obtained even when you make those simplifications. So when you make some kind of simplification, you are losing information, you are neglecting some things. So after doing that, whatever differential equation you come up with, that is representing an idealized situation, which is not the real situation. However, it is close to the real situation. So if you are able to solve that differential equation, then the solution will tell you something about that situation, but approximately. Always remember this, no matter whatever we do in any kind of science, it is always an approximation. Exactness exists only within mathematics itself. When you try to apply mathematics outside, some kind of approximation or simplification must be involved. So even while formulating, there is some kind of dumbing things down, if I want to say so, by neglecting some information. And sometimes actually this becomes necessary also. Say you are studying some kind of problem, and some aspects of the problem will really be not necessary for what you are trying to formulate. So they can completely be ignored, and you can formulate the problem leaving those complexities. But no matter whatever you do, your differential equation itself will only approximately represent the situation, and then you may not be able to solve the differential equation exactly. Already the equation itself is an approximation, but even after that, you may not have any way of solving it exactly. You may only be able to solve it again approximately. So now the solution that you are getting is still an approximation to the supposed solution that the differential equation has out there somewhere. But even after this amount of approximation or this amount of simplification, still from that approximate solution itself, the scientist, the physicist, chemist, whoever is using this thing, they are still able to say many things about the situation. That is the power of these things. And in some cases, you won't really be able to solve the equation at all. Sometimes approximate solutions are also very crude, so that they become useless. Even then, using the theory of differential equations, you can still say something about these solutions that should be there out there somewhere. Something qualitative or even something quantitative without even finding the solutions. And then you can use that information to say something about what the differential equation represents. Okay, so we are going to see these things, and slowly what we will do, the theory part of this section ends now. After that there are exercises, because we haven't really seen anything other than the classification in this section. So obviously these exercises will again ask us to classify some equations into linear, non-linear, these things, okay. But after that, we will slowly consider specific types of equations, and then we will see if they can be solved. So we will build up the theory slowly, where we can solve this type of equation, then a slightly more general type, a slightly more complicated type, linear, non-linear. In general, non-linear equations are extremely difficult to study. So as I said just now, that while formulating the equation, there itself, in that process itself, there are approximations. But sometimes when you have an equation which is non-linear, usually you can approximate the equation itself by considering a linear version of it, by linearizing it. So now you actually have another equation which is linear, but which is somewhat like the non-linear equation, and then you try to solve the linear equation. It's not easy that you just simply formulate an equation, you solve it, and that's it. It's not like that. Okay, so we will see all these things. So let me just end the video here itself. Tomorrow also there is an upload, and tomorrow I will be solving that. I think last Wednesday also I solved some number theory problems requested by someone, requested by Daniel. Yeah, tomorrow also I will be solving some more of these things. So see you tomorrow, Daniel, with these things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.